In our previous video, we had this example 8. Two water pipes working together to fill a container. And you see that the work was additive in that case. We had A's work plus B's work gave us the completed job. Okay, so A had a certain rate. In the case of that example, it took 6 minutes to fill that tank. And then pipe B had a certain rate. And in the case of the example, it took 8 minutes to fill the tank. And we worked the problem like that, where the two were working together. Well, what if the two are not working together? What if I've got one pipe trying to fill a tank, and then I got, maybe a hole in the bottom of the tank, and I'm losing water? Well, as you can suspect, the pipe filling the tank is going to be a positive amount of work, but then I'm going to subtract away the amount of work from the pipe or the hole in the tank that's losing the water, to use the tank example again. Okay, and our next example does that. Okay, so in this case, we're going to have to subtract something. Okay, so if we take a peek at the next problem, which is example 9 on page 344, let me read it and then I'll work it. A faucet fills a tank in 6 minutes. I don't know if there's a glare on your screen or not. It's hard for me to tell. A faucet fills a tank in 6 minutes. A drain empties the tank in 8 minutes. So if you think about it, the faucet's working harder than the drain, so to speak. The faucet can fill the tank in 6 minutes, but it would take the drain 8 minutes to empty the tank. Okay? Both the faucet and the drain are open. Okay, and how many minutes will the tank start to overflow if the faucet is not turned off? So we're going to start with an empty tank, but the drain is open at the bottom. We're going to start adding water from the faucet, so some water is immediately going to leak, going to lose out down the drain. However, we're filling it faster than it's draining, so eventually we will fill the tank, and that's the question. How many minutes until the tank is full and starts to overflow? Okay, so let's look. We need to have the rate of work of the faucet, right? Faucet. Well, what's the faucet doing? What's the rate that the faucet is operating? It fills the tank in 6 minutes. So one tank per, rates are always a division problem, right? Per 6 minutes. That's the faucet's contribution. One tank per 6 minutes. Well, what about the drain? It can drain one tank in, it was 8 minutes, right? Yeah, 8 minutes. Okay? So the two are going to be working together, but they're not helping one another. They're working against one another. Okay, so I'm going to have this amount of, let's just pretend I'm trying to fill the tank. One tank in 6 minutes times some t for time, that's going to equal how much of the tank is full. Okay? If t time were 6 minutes, if that was the only problem here, and I put 6 minutes in for t, you see the 6 minutes are going to cancel, and I'll have one tank left over, and that's what it would take to fill the one tank, right? Okay. But that's not the whole story. I'm filling it with the faucet, but now I'm subtracting away the drain. What's the drain doing? Well, it's trying to drain one tank in 8 minutes. Okay? And I'm going to let this process run for how long? For t minutes. I don't know. That's the question. How long are we going to let this go? T stands for the time now. Okay? So I'm going to be adding to the tank for a certain amount of time. I'm going to be subtracting away from the tank for a certain amount of time. And I want to know, when will I get a value of one tank? When will the tank be full and then, of course, start to overflow, which is the way it was worded. Okay, so this is my problem. 1/6 t, if we drop the units, minus 1/8 t equals 1. It's a fractional problem. Okay, remember with a fractional problem, we can clear those denominators right out of there. It's a little easier. It's not necessary. I could go ahead and do this subtraction and find my common denominator and all that good stuff just fine. But another way to tackle a problem like this is to clear out the fractions. So let's practice that. We still need to find the common denominator between 6 and 8. Okay, we always want to find the lowest common denominator. In this case, that'll be a 24, right? I multiply through the problem, numerator only, by 24. So I'll stick a denominator of 1 under there just to convince myself of that, so I don't forget. So now I got 24 over 6t minus 24 over 8t equals, well, you can see all this mess is just going to turn into a 24. All right, well, now look. All these fractions divide away now because this just becomes 4t minus 3t equals 24, which 4t minus 3t is 1t equals 24, so all of a sudden the problem is solved. I'm solving for 1t, I've got 1t, 24. Time was in minutes, so it will take 24 minutes to fill that tank if I have the faucet running and the drain open. Okay? Pretty good. Okay, we have a rate times time. Okay, rate times time gives us a lot of information. If it were a vehicle moving problem at a constant speed, the distance equals the rate times the time. Well, in this case, it's filling a tank. The rate I'm filling the tank times the time, that's how much I'm going to fill. But in this case, I was filling and subtracting away at the same time, so a little more complicated. All right, sweet. Let's check out our next example. Our next example is a decimal problem. Example 10 on 345. Now again, just like we had the option up there with the fractions, you know, decimals are not such a big deal, especially with the calculator. Okay, here's what we've got. 0.38 plus 1.1y equals 0.6. We could just work it with the decimals. It's really, like I said, not a big deal. Okay, especially with our calculator. What do we want to do? We want to get y all by itself. So I want to subtract away the 0.38 from both sides. Okay, now maybe I got to stop and think a minute about how to take 0.6 minus 0.38. If I have any doubt, calculator is my best friend. What do I get there? I get a 0.22. So 1.1y equals, I said 0.22, right? Yeah, 0.22. Divide by 1.1. Divide by 1.1. Again, calculator's our best friend here. What are we going to get? We're going to get 0.2. Okay, we're done. It's easy. There's an option though. Maybe you're just the kind of person who doesn't like to deal with the decimals. Maybe you don't have your calculator. There's a way out of this thing. Now let's write the problem again. I better start fresh here. 0.38 plus 1.1y equals 0.6. I need to ask myself a question. Look at all of my decimals in the whole problem, and I have to ask myself, what would it take to make those decimals turn back into whole numbers? Okay, in other words, the 0.38, I would have to shift that decimal 2 places to the right, and then it would be a 38, whole number. Here I only need one shift to turn that into an 11, and here I only need one shift to turn that into a 6. So I have to identify the greatest number of shifts required throughout the entire problem. So in this case, it's 2. Okay, so I'm going to multiply by that greatest number of shifts. I'm going to multiply by that power of 10. So 2 shifts means 2 powers of 10, or 100. Both sides of the equation I'm going to multiply by 100. Well, what did that do for me? That gave me a 38 there. It gave me a 110y, right, equals 60. 2 powers, 2 shifts. Okay? All good there? The numbers are a little bigger now, but the decimals are now gone. Okay, so maybe that makes you more comfortable. You'll see we're going to get the same thing. I'll go ahead and pull out the calculator here. 60 minus 38. What do we get there? 22. We had 0.22 before, remember? So you see the numbers are going to be very similar, just decimal shifts. 22 divided by 110. And if we divide by 110 equals 0.2, the same answer we got the other way. Okay, so it changed the equation into what's called an equivalent equation by multiplying through by 100, but equivalent equation, same answer. Okay? All right, sweet. The middle of page 345 brings up a classic formula that's used to calculate simple interest. Okay? I equals P PRT. Lots of alphabet soup there, but we're only going to have one unknown in our problem, okay? I, in this case, stands for interest. Okay, I'm going to put some money in the bank and I'm calculating the interest, right? Well, what am I going to put in the bank? I put in P, the principal. Okay? I'm putting it in the bank and the bank is going to give me some interest rate, right? R stands for rate. And I'm going to leave it in the bank for a certain amount of time. Okay, so in this case, the letters of the formula were kind of cleverly chosen to make sense for us. That's not always the case. Sometimes you're like, well, you know, well, what are these letters? Where'd they get these letters? They don't really make sense to what we're doing. In the world of science, a lot of times Greek letters are thrown in there too, so it can really get to be confusing. And we had a couple of problems actually with Greek letters already. But okay, this is pretty straightforward. Interest equals principal times rate times time. This is called simple interest. Okay, there's another more complicated form of interest called compound interest, and we don't really get to that, at least now in this part of the course. Probably not at all. Okay, so let's look at a problem. Example 11 says, a $1,000 investment, here, let me pull the book over. Example 11. A $1,000 investment is made for 2.5 years at 6.25%. Find the amount of interest. Okay, so we're given all this information. We're given 3 of the 4 unknowns, right? So that's easy. We are going to take $1,000 and we're going to invest it. We're calculating the interest. So that takes the principal, which is $1,000, times the rate, which is given to me as a percentage, 6.25%. Now I got to be careful about the rate. And the book did not even attempt to trip us up. The 6.25%, that should really say percent per year. Okay, and the catch, the rips with a problem like this is you might be given the rate in terms of a percent per year, but then the time might be given to you in months or days or something else, and then you have a mismatch of your units that you have to worry about. Okay, in this case we don't have that. Okay, that's really percent. I'm going to go ahead and write it per year. Okay, times what? It's got to be times some kind of year, so the years cancel. In this case, 2.5 years. Again, if it said months, then we would have a mismatch of units, and I couldn't just cancel those units away, and it's not then just a straight multiplication, because I would have to make an adjustment from months to year in here somewhere. Okay, so always watch out for that, but in this case, not a problem for us. Okay, well, we can do a little... maybe make our life a little easier by turning that into a decimal. So it'd be 0.0625. We could turn that into a decimal, 2.5. Now it's all kind of straightforward calculations for us on our calculator. And if we run all those numbers, I'll just look at the book here, we're going to get $156.25. Okay? That is the amount of interest we would earn if we took $1,000 and put it in an account that pays 6.25% per year, and we left it in there for 2.5 years. Okay? Simple interest. All right. Again, most banks and lending institutions pay what's called compound interest. Okay, and it doesn't show up right now in our book, and it's probably in there somewhere, but I don't think we'll get to it in this course. It's a little more involved formula. It's got an exponent we got to deal with, and then depending on the compounding period, the equation could even go even a little more complicated, if you will, involving this mathematical constant lowercase e. And again, I don't think lowercase e is going to show up in our class. Okay, that's called the Euler number, or some people pronounce it Euler. Okay, that little e, I mean, we all know Greek letter pi, right? Little e is another number kind of like Greek letter pi. It's a irrational number. It's a decimal that goes forever. It's approximated 2.72, okay? Little e, but it's one of those numbers that goes on forever, and it shows up everywhere in not only high-level math, but in a lot of applications, one of which is continuously compounded interest, okay? It shows up in all this virus talk with the exponential growth of this virus. You might see that if you ever see somebody paste a formula, they probably don't do that on the news, but if you ever see someone paste a formula out there, you might see that little E as part of the formula, and you'll say, oh, what's that? It's a number, the Euler number. Okay, awesome. We have one more example in this section, and then we're going to be done with section 7.3. Again, you're not responsible for that, just a simple interest problem. Okay, 7.3, all right, back to electricity. Example 12, let me pull the book over. The formula for voltage is wattage divided by amperage. Okay, V equals W over A. This is for what we call single-phase circuits, if you know anything about electricity. Three-phase power, there's more to the story, but this is for single-phase power, okay? Voltage is wattage divided by amps, so the way I more commonly would see it written would be that, let me make sure I use the symbols exactly what they do. They use W for wattage. Sometimes people use P for power there instead of W for wattage, but okay. Watts equals volts times amps, okay? Now that's not the formula in the book. The formula in the book is solved for V. Okay, we know how to solve for V. We did some of these, right? How do I solve for V? Well, I got to divide by A. Divide by A. Okay, A's cancel over here. I get W over A equals V. And of course, we can always just turn a formula around. I can say V equals W over A. Okay, that's the formula in the book. Okay. You can always shuffle formulas around, okay? Get in the habit of doing that. It's just our basic algebra skills, but we have a lot more symbols instead of numbers, and it looks more confusing that way, but it really shouldn't be. All right, so here's an example. We're given this formula. Find the voltage, let's put it back here. Find the voltage to the nearest hundredth, so we're going to have to round, needed for a circuit that's 1,280 watts with a current of 12.23 amps. Okay, so 1,280 watts, so volts, we're calculating volts, equals 1,280 watts. Okay, W for watts, divided by 12.23 amps. Okay, and I don't want to confuse you with what I just did. Here, the W and the A, that's the symbol that stands for the wattage and the amperage. Here, it's just a unit, watts divided by amps, okay? And watts divided by amps equals volts. So, and it's really not important to our lesson that we know that, and I'm going to write it again without the units just to drop any possible confusion. I did not leave the variables there and then stick a number in front of them like coefficients. In this case, the W and the A, that's the unit that goes with the number. In this case, it's the variable. Okay, so let me, again, to avoid the confusion, just forget I did that. Okay, the book did not do that. Take the watt number divided by the amp number, and you're going to get volts out of the deal. Okay, so if we take that, let me bust out the calculator. It asks us to round to the nearest hundredth, so we're probably going to get some big goofy decimal here. Divided by 12.23 equals, what do we get? 104.66067. Okay, of course, if these were measured values, those aren't all significant digits, right? Remember from those days of significant digits. But in this case, we're told what to round to. The nearest hundredth, 10th, hundredth, so I'm rounding to that place there, which means I'm going to look beyond that place there. I'm going to look at that 0 to make my decision on whether or not that stays a 6 or gets bumped up to a 7. And of course, in this case, it would stay a 6. Okay, so now the book now even sticks a V over there. In that case, V stands for volts. It's not the variable, it's the unit. So let's not get too confused about that, though. Okay, that's my answer. Okay, sweet. That's it for 7.3. 7.4, the title is Inequalities and Sets. We're not going to dwell too much on the sets part, though. Okay, we're going to just talk more about inequalities, and 7.5 is also more inequality stuff. Very similar to equations, except they're unequal. Okay, so I'm going to have an unequal sign, an inequality sign. Greater than, less than, greater than or equal to, less than or equal to. Those are the inequality signs. We're going to be seeing those that show up in what would otherwise look like an equation. Okay? Stay tuned.